Welcome back to the deep dive. Today, we are opening up a piece of technology that I can almost guarantee you have touched, interacted with, and probably been slightly addicted to within the last 24 hours.
Oh, definitely.
It is the mechanism that powers your morning routine, your procrastination breaks, and, your late night doom scrolling.
It is the digital equivalent of the slot machine, the town square, and the morning newspaper, all sort of fused into one infinite loop.
We are talking about the news feed, the infinite scroll. It's the backbone of Facebook, Instagram, X formerly Twitter, LinkedIn. I mean, even apps that aren't social networks seem to have a feed now.
They all do.
And on the surface, it feels incredibly simple. You open the app, you see a picture, you scroll down, you see some text, maybe you hit a like button. It feels trivial.
And that illusion of triviality is the hallmark of exceptional engineering. I mean, it really is. Because if you actually look at what is happening under the hood, especially when you scale it up to the level of the big players, it's anything but simple.
Right.
It is a masterpiece of distributed systems, data synchronization, and, frankly, psychological optimization.
We have a massive stack of documentation here today, outlining the system design for a hypothetical mobile newsfeed app. And we aren't talking about a small hobby project. What's the target scale we are looking at here?
The prompt for this deep dive is to design a system capable of handling 500 million monthly active users.
500 million people?
500 million. And that number, it just changes the physics of software development. It really does.
How so?
If you build an app for 500 people, you can do almost anything. You can be inefficient, you can have a slow database, you can make mistakes. But at 500 million, a 1% error rate means 5 million angry users.
Wow.
A millisecond of latency multiplied by billions of requests is, literally years of wasted waiting time for your user base.
So the mission today is to deconstruct this architecture. We're going to look at how we move data from a server farm halfway across the world onto a device that fits in your pocket, and how we make it feel instant, reliable, and smooth, even when the internet connection is, complete garbage.
Exactly. We're going to look at the invisible protocols, the magic tricks used to mask latency, and the rigorous logic required to handle offline states, because that's where the real magic is.
But before we start building, we need to know the rules. We need to put a box around this. What are we actually building? Because newsfeed is a broad term. Are we building a TikTok clone? Are we building a live streaming platform?
No. And this is a crucial part of system design, defining the boundaries. If you try to build everything, you build nothing. So for this specific design document, we are focusing on a classic feed.
Okay, so classic feed, what does that mean?
Think of the main Facebook timeline or the standard Instagram feed, a vertical list of posts.
Got it. Okay, so what are the functional requirements? What does it have to do?
They're straightforward, but they're heavy. First, it's an infinite list of posts from entities you follow, people, pages, whatever.
Okay, the scroll itself.
Right. Second, the content needs to support rich text, bolding, italics, links, and media attachments.
Yeah.
We need photos and videos.
Of course. And the third?
Social interaction. You need to be able to like and share directly from the feed. Those are the core table stakes.
And just as important, what are we explicitly ignoring? What are we kicking out of scope?
Okay, so we are marking live video and real-time chat as out of scope.
Why is that?
They just require completely different architectural patterns, usually involving persistent socket connections like WebSockets. It's a whole other deep dive.
A different can of worms.
A huge can of worms. We're also setting aside the authentication, logic logging in, two-factor auth, all that. We're going to assume the user is authenticated, and we have a token. We are laser focused on the mechanics of the feed itself.
Okay, so we know what it does, but how does it need to perform? I see the term non-functional requirements in the notes here.
I call these the 4 pillars.
Wow.
If you miss one of these, the app fails, no matter how good the features are.
All right, lay 'em on me. What's pillar number 1?
First is scalability. As we said, 500 million users. The system must handle spikes. If the Super Bowl is happening, usage might triple. The system can't crash. It has to bend, not break.
Right. Elasticity.
Pillar number 2 is performance. This is all about the feel. We need 60 frames per second scrolling. If the feed stutters, what we call jank users, subconsciously perceive the app as low quality.
I know exactly what you mean. It just feels cheap.
It does. Third is reliability. It has to work on patchy networks. This is the subway tunnel test. Can the user still have a good experience when their connection is dropping in and out?
And the 4th pillar?
Data efficiency. In many parts of the world, data is expensive. If we burn through a gigabyte of data just to show a few memes, people will uninstall the app. We have to be miserly with every single byte.
Okay, 4 pillars. Scalability, performance, reliability, and data efficiency. Got it. All right, let's get into the blueprints. Segment 1, the API and data strategy.
Let's do it.
We have the phone, the client, and the server. They need to talk. My instinct, looking at modern tech trends, is to use something like GraphQL. It's trendy, Facebook invented it, and it lets you ask for exactly the data you need. No more, no less.
GraphQL is incredibly popular, and you're right, for complex nested data structures, it is fantastic. It absolutely solves the problem of overfetching, downloading data you don't use, and underfetching.
Underfetching.
That's where you have to make 5 different requests to get all the data for just one screen. GraphQL lets you bundle that all into one trip.
So why does this design document reject it? It says, here we are going with HTTP and REST APIs. That feels, I don't know, a little old school.
It is old school, but it's also battle-tested. And the primary reason the architect chose REST here is a single massive advantage: caching.
Caching. Explain that.
Think about how HTTP works. The protocol itself has built-in mechanisms for caching at the network level. You have headers like ETAG and cache control.
Wow.
If I request a resource at a specific URL, intermediate servers, proxies, CDNs, even your local ISP can look at that URL and the headers and say, hey, I already have a copy of this. It hasn't changed. I don't need to bug the main server.
So you're offloading the work to the internet itself.
Precisely. And GraphQL doesn't really do that, does it?
Well, how does that work with GraphQL?
GraphQL usually operates over a single endpoint, like GraphQL, and it almost always uses POST requests. To a caching proxy, every single request looks unique or, completely opaque. It can't look inside the POST body to figure out what you're asking for.
Ah, I see.
So you can't easily cache GraphQL responses at the network infrastructure level without specialized tooling. By using REST, where every resource has a unique URL, like post 123, we leverage 50 years of internet infrastructure that knows how to optimize that traffic.
So we're trading the flexibility of the query for the raw efficiency of the existing internet infrastructure.
That's the trade-off. And for a news feed, where content is read millions of times more than it is written, that read caching is absolutely vital for performance and for cost.
Okay, that makes a lot of sense. And we're using JSON for the data format.
Yes, JSON over HTTP.
I saw a note here about protocol buffers protobufs. Those are binary, right? They're smaller and faster than text-based JSON. If we care so much about bandwidth, why aren't we using those?
That's a really valid trade-off to question, and some teams do choose protobufs. They are indeed more efficient on the wire.
So what's the catch?
The catch is complexity in debugging. You can't just open a protobuf file and read it like you can with JSON. It requires strict schemas, compilation steps, and specialized tools. If something goes wrong, it's just harder to figure out what the server sent.
So it's a developer experience issue?
It is. For this design, the argument is that JSON is good enough. It's human readable, which is a huge benefit. It's easy to debug. And with gzip compression enabled on the server, the size difference for a typical newsfeed payload isn't usually the bottleneck.
What is the bottleneck then?
The media. The images and videos are the real bandwidth hogs, not the text JSON. We're talking orders of magnitude difference.
That makes sense. Optimize the big things, don't sweat the small stuff yet. Now, this next part is something I've struggled to wrap my head around in the past. The pagination problem.
Ah, yes. The bane of many a developer.
I understand pagination in a book, page 1, page 2. I get it on Google search results. Why is it so hard for a dynamic, real-time news feed? Can't we just say, give me the first 20 posts, then give me the next 20?
You can,
Yeah.
and that's called offset pagination. You're telling the server, skip the first 20, give me the next 20. It works perfectly for static lists.
Like books on a shelf.
Exactly.
Yeah.
If you go to a library, the books on the shelf don't move. You look
Yeah.
at the first 10, walk away, come back an hour later, and the 11th book is still the 11th book.
Right, but a news feed is not a library shelf.
It's a living stream. It is highly volatile. Imagine you were looking at the top 10 posts on your phone. You are effectively on page 1. While you are reading those posts, 5 new posts are created globally and shoved onto the top of the stack on the server.
Okay, so the whole list gets pushed down.
Exactly. The server inserts 5 new items at the top. This means the post that was at position number 11, which should have been the start of your page 2, is now at position number 16.
I see where this is going. So if I ask the server for page 2 now, which is items 11 through 20.
You are going to get items 11 through 15, which are the exact same posts you just saw at the bottom of page 1 a few seconds ago. They've just shifted position.
Duplicate content. I hate when that happens. I scroll and see the same 3 things again and again.
It's a terrible user experience. This is called drift, and it works in reverse too. If a moderator deletes a bunch of posts while you are scrolling, the list shrinks up.
And then what?
When you ask for the next page, you might skip over content entirely because it's slid into the page 1 slot that you already finished. You just miss posts and never even know it.
So offset pagination is just fundamentally unreliable because the ground is constantly moving beneath our feet. So what's the fix? The notes mention cursor-based pagination.
Right. We need an anchor. We need something that doesn't move. Instead of telling the server and offset a number, we give it a place.
What do you mean by a place?
Instead of saying, give me items 21 through 40, the client says, the last post I saw had an ID of hashtag 8945. Give me the 20 posts that come after I tag 8945.
Ah, so you're using the last item as a bookmark.
Exactly. Because even if a million new posts come in at the top or 10 posts get deleted from the middle, post I tag 8945 is unique and stable. It points to a specific record in the database.
So the query is stable regardless of what happens to the rest of the list.
It's stable. The query is simple. Where creation time timestamp of last post, order by creation time deci limit 20. It's incredibly efficient for the database.
Is it really faster?
Oh, much faster at scale. Offset pagination often requires the database to count through all the previous rows just to find where to start. Offset 1 million is a very slow query. A cursor-based query on an indexed column is lightning fast.
This brings us to the IDs themselves. I skimmed this part, but it seems surprisingly complex. Why can't we just number the posts 1, 2, 3, 4, and auto-incrementing integer?
In a single centralized system, you can. The database just adds one every time. But remember our scale, 500 million users.
Right. We have lots and lots of servers.
We have thousands of servers. We likely have database shards, meaning the data is split across many different physical machines. If we had to ask a single central authority for the next number every single time a post was created,
that authority would melt. It becomes a massive bottleneck.
It's the definition of bottleneck. The entire system would grind to a halt waiting for that one number generator.
So the servers need to be able to generate IDs on their own without talking to each other.
Yes. They need to generate IDs independently, but those IDs still need to be unique globally. And ideally, they should be roughly sortable by time. We don't want post ID tag 100 to be from today and post ID tag 101 to be from last year. That would break our cursor logic.
So how do we do that without talking to a central brain?
We use a system like Twitter's Snowflake ID. It's a 64-bit integer. It's not just a random number. It's highly structured. It's a brilliant piece of engineering.
Okay, break down the structure for me. What's inside that 64-bit number?
So the first bit is reserved. The next 41 bits are a timestamp, the number of milliseconds since a specific fixed point in time, what we call an epoch.
And that gives us the time sorting for free.
Right out of the box. If the ID is bigger, the post is newer. That's the most important part.
Okay, so that's 42 bits. What about the rest?
The next 10 bits represent the machine ID. Each server that can generate IDs is given a unique code from 0 to 123. This ensures that server A and server B can never generate the same number, even at the exact same millisecond.
Because their machine IDs are different.
Exactly.
Yeah.
And the rest.
What's left?
The last 12 bits are a sequence number. This allows a single server to generate up to 4,096 unique IDs within the same millisecond without colliding with itself. It just increments that counter for each ID it creates.
So it's like a composite key packed into a single highly efficient number, time plus machine plus sequence.
That's a perfect way to put it. It allows for high throughput distributed generation with zero coordination required between servers. It is the standard practice for systems of this size.
Okay, we've got the data structure sorted out. Now let's talk about what we're actually downloading. If I scroll past a video, I don't want to download the 4K version instantly. That kills my data plan.
No, you definitely don't. And this is where that two-tier data model comes in. We split the data for any given post into two separate objects, post preview and post detail.
Okay, what's the difference?
The post preview is what you see in the main feed while you're scrolling. It's designed to be incredibly lightweight.
What's in it?
Just the bare essentials, the text, maybe a truncated version of it, the author's name and profile picture URL, the likes count, And this is key. Only a low-resolution thumbnail URL or a highly compressed video preview.
So the app is only sipping data while I scroll?
Exactly. We're being as frugal as possible.
Yeah.
We only fetch the post detail object, which contains the high-res image URLs, the full comment tree, the heavy metadata, when the user explicitly taps to extend the post or stop scrolling on it for a second or two.
A user-initiated action.
Right. We delay loading the heavy stuff until we're pretty sure the user actually wants it.
Let's move to segment 2, the skeleton. The architecture inside the phone itself. We have a diagram here showing the client architecture. It mentions UDF, unidirectional data flow. What is that?
UDF is a philosophy, really, a design pattern. In the early days of app development, we had what I sometimes call pinball architecture.
Pinball. I like that.
A network request would come in and directly update a piece of the UI. Then a user would click a button, which would update a variable over here. Then a background timer would fire and update the UI again from somewhere else.
So data was just flying everywhere.
It was chaos. The view was modifying the model was modifying the view. It was completely impossible to debug because you never knew who changed the data or why. The state of your app was unpredictable.
Spaghetti code.
The worst kind. UDF cleans this up with one simple rule. Imagine a river. Data flows only one way. Down from the top layer, which is your data layer, down to your business logic, and finally down to the UI.
So it's a one-way street.
A one-way street for data. And what about user actions if I tap a button?
Events flow up. The UI sends an event saying user tapped like.
Yeah.
That event goes up to the logic layer, which processes it and decides to update the state. The new state then flows back down to the UI, so the UI never, ever updates itself directly.
Never. The UI is dumb. That's the goal. It's a passive screen. It just renders whatever the current state tells it to render. This eliminates an entire class of bugs where the UI gets out of sync with the underlying data. It's predictable.
And sitting at the bottom of this data flow is the repository. What is its job?
The repository is the traffic controller. It's the gatekeeper for all data in the app. The UI asks the repository, give me the feed. The repository is the one that decides where to get it from.
What are its options?
It asks a series of questions. Do I have this in the local database? Is it fresh enough? No. Okay, is the network available? Yes. Okay, I'll fetch it from the network, save it to the database, and then give it to you.
So the UI doesn't know and doesn't care if the data came from the cloud or a local file.
It has no idea. That abstraction is critical, and it seems really important for segment 3, which is the part I'm most excited about, the subway tunnel scenario. Offline support.
Yes.
This is where good apps separate themselves from great apps. This is the real test.
So let's paint the picture. I'm on the subway. I have a connection. Everything's working. I scroll a bit. Then the train goes into a tunnel. Connection dead. In a bad app, what happens?
In a bad app, you scroll a little further and you see a white screen. Or a spinning wheel that never, ever stops.
A spinner of death.
We've all seen it. But in this design, the goal is that you, the user, shouldn't even know you're offline, at least for a while.
How is that even possible?
It requires a fundamental shift in how we treat the network. In a naive app, the UI asks the network for data. If the network fails, the UI shows an error.
That seems logical. If I can't get data, I show an error.
It is logical, but it's fragile. It makes for a brittle user experience. In our design, we implement the single source of truth pattern, SSOT.
Okay.
And the golden rule is this. The UI never displays data from the network.
Wait, say that again? The newsfeed app doesn't show data from the network. Where does it get it from then?
Never directly. The flow is always this. The app fetches data from the network. It immediately saves that data into a local database on the phone, using something like SQLite or Room on Android.
Okay.
Then the UI observes the database. It listens for changes in the database.
I see. So the database is the buffer, the middleman.
The database is the only truth. The network is just a detail, a way of getting new data into the truth. When the network brings in new posts, it dumps them in the database. The database then notifies the UI, hey, I have new stuff. The UI wakes up and updates.
So if the network cuts out in the subway tunnel...
The UI doesn't care. It's still just staring at the database.
Yeah.
If there are 100 posts in the database, the UI will happily show them. You can keep scrolling through everything you've already cached. You can even write comments or like posts.
But wait, how can I like a post if I'm offline? The server doesn't know.
You are interacting with the local copy. You're telling your local database, mark this post as liked. We'll get to how that syncs up with the server later. But for the user, the app remains fully functional. It feels alive.
Why use a relational database like SQLite for this? Why not just save a big JSON file to the disk Or use a simpler key value store. Wouldn't that be faster?
Key value stores are very fast for simple lookups, like getting a user profile by its ID. But they are terrible for complex queries. And a newsfeed is a surprisingly complex query.
What kind of query?
We need to say, give me the top 20 posts, ordered by creation time, where the author is not on my block list and where the post does not contain muted keywords. SQL is built for exactly that kind of structured query. Trying to do that filtering with a giant JSON file in memory would be slow and incredibly memory intensive.
Okay, so SQL gives us the query power, but we can't keep filling the database forever. My phone has limited storage. It's not a server.
Correct. You'll run out of space very quickly. We need eviction policies. We need a janitor that comes around and cleans up old data.
How does the janitor decide what to throw out? What's the logic?
We usually combine a few strategies. It's a hybrid approach. First, LRU, least recently used. If a post is 5,000 items down the list and you haven't looked at it in a week, it's probably safe to delete it from the cache.
Okay, that makes sense.
Second, we use a TTL time to live. We might have a hard rule that says anything older than 30 days gets purged from the local cache, period, even if you saw it yesterday.
But we should always keep something, right? So the app isn't just blank when you open it.
Yes, and that's the third part. We keep a minimum threshold. We always want, say, at least 50 posts in the database, no matter how old they are. That way, if you open the app in airplane mode, you immediately see content. It might be yesterday's content, but an app with old content is always better than an app with an empty screen.
Now, you touched on something really interesting, interacting while offline. This brings us to segment 4, the magic trick, optimistic writes.
This is one of my favorite topics. It's purely about the psychology of speed.
I tap the like button on a post. The heart icon turns red instantly. There is zero delay.
But we know that's a lie, don't we? It has to be. The signal has to go from your phone to the cell tower, get routed to fiber optic lines, maybe across an ocean, to a data center, get processed by the server, written to a database, and then a confirmation has to come all the way back.
How long does that take in reality?
On a good connection, maybe 200 milliseconds.
Yeah.
On a bad one, 500 milliseconds, maybe a full second.
If I had to wait half a second every single time I like something, it would feel sluggish and broken.
Terribly broken.
Oh.
So we lie. We perform a magic trick. The moment you tap that button, the local app says, I'm just going to assume this will work.
It's being optimistic.
It's being optimistic. It updates the local database immediately. It changes the state from is liked, false to is liked.
True.
The UI sees that database change and instantly paints the heart red. The user gets that immediate satisfying feedback.
But in the background, what's happening?
In the background, we create a task.
Oh.
We put a request in a special pending queue in our database. We create a record that says user wants to like post hashtag 456. The app then tries to send that request to the server whenever it can.
And if I'm in that subway tunnel with no connection?
The request just sits in the queue. It's persisted. Even if you force quit the app and open it an hour later when you're back on Wi-Fi, the app's startup logic will check that queue. Oh, hey, I still need to tell the server that we like this post. And it sends it off.
That's brilliant. But what if the server rejects it? What if, I don't know, the post was deleted by the author while I was in the tunnel?
That's the conflict scenario, the moment of truth. If the server comes back and says, error 404, post not found, we have to roll back the change. We have to face reality.
So what does that look like?
We have to revert the local database. The red heart turns back to gray. The like count goes down by 1.
That seems like it could be jarring for the user. They thought they liked it.
It can be. Sometimes we show a little toast message, that little gray box at the bottom of the screen that says could not like post. But honestly, for an action like a like, it succeeds 99.9% of the time. The optimistic approach is worth the risk for the huge perceived performance gain.
Okay, but we have to be careful not to spam the server if the network is just flaky, right? If I send a request and it fails, I shouldn't just spam retry 1,000 times a second.
Right. That's how you accidentally DDoS your own backend and get your IP address blocked.
Yeah.
We use a strategy called exponential backoff.
Explain the math there. How does that work?
It's simple but very effective. We try to send the request immediately. If it fails, we wait 1 second and try again. Still fails. We double the wait time. We wait 2 seconds. Fails again. We wait 4 seconds. Then 8, 16, 32, and so on, up to a maximum cap.
Why do that?
It gives the network, or our own servers, time to recover if they're overloaded without clogging the pipes with a constant stream of failing retries. It's a much more polite way to handle failure.
Let's move to our last segment. Segment 5, visuals and performance. We've got the data, we've handled the network. Now we need to actually draw the pixels on the screen.
The final step.
The requirement is rich text, bold, italics, links.
My developer brain immediately says HTML. The web solved this problem decades ago. Just put a little browser window, web view, in each post cell. Easy.
No, absolutely not. Please, nobody do that. That is the cardinal sin of mobile performance.
Why? It's so easy for the developer.
It is easy for the developer, but it's terrible for the phone and the user. A web view is an incredibly heavy component. It's essentially launching a mini Chrome browser. It consumes a lot of memory. It has its own complex rendering loop.
And if you have a list,
If you have a list of 50 posts and each one is a mini browser, your scrolling performance will be a disaster. It will feel slippery and slow and drain the battery. It's just not the right tool for the job.
so we have to do it the hard way, native rendering.
We have to. We take the HTML string from the server because HTML is a great standard format for describing rich text. But on the client, we parse it manually. We don't render it as a web page.
So what do? We walk through the string. Oh, here is a B tag. We translate that into a native formatting span, like a style span in Android, or an NS attributed string in iOS. Here's an O tag. We make that a clickable link span.
So we are translating the web language into the phone's native text rendering language on the fly.
Exactly. And native text views are incredibly optimized. They use very little memory, and they render almost instantly. The difference in performance is night and day.
Is there a security risk there? I mean, if we are parsing HTML from user-generated content?
Huge risk.
Yeah.
A massive risk. It's called cross-site scripting, or XSS. If a malicious user posts a comment with a script tag in it, and we blindly parse and execute it, they could potentially steal your session token or other private data.
So what's the defense?
You have to sanitize the input. Before we even try to render it, we run the HTML through a sanitizer that strips out any dangerous tags like script, iframe, on-click attributes, anything that could execute code. We only allow a safe subset of tags like bin.
Now let's talk about jank. You defined this earlier as stuttering scrolling. What physically causes that on the device?
To understand jank, you have to understand the frame loop. Your phone screen, if it's a standard one, refreshes 60 times a second. That means the phone has about 16.67 milliseconds to do everything. Calculate layout, measure text, decode images, and draw the new frame.
16 milliseconds is not a lot of time.
It's an incredibly short amount of time. It's blink of an eye fast. If your code for drawing a single frame takes 20 milliseconds to run, the phone misses its deadline. It has to drop a frame, it shows the previous frame again.
And the user sees that as a freeze, a stutter.
That is jank.
So the Goldie rule is don't do heavy work on the drawing thread.
Don't block the main thread. That's the mantra of every mobile developer. Database queries, JSON parsing, image resizing, heavy calculations, that all has to happen on background threads. The main thread should only be for taking prepared data and putting pixels on the screen.
And what about the memory issue? We have thousands of posts in our feed. If I create a unique view object for every single post, I'll run out of RAM in seconds.
You will. This is where a fundamental technique called view recycling comes in. Think of it like a conveyor belt, or maybe plates at a buffet.
Okay, I like the buffet analogy.
Your screen can only fit, say, 5 posts at a time. So the system only creates maybe 7 or 8 view holders, the empty plates. As you scroll up, the post that goes off the top of the screen isn't destroyed.
So what happens to it?
We take that empty plate, that view, we scrub the old data out of it, move it to the bottom of the list just before it scrolls into view, and we fill it with the new posts data.
So we are constantly reusing the same few empty shells.
Constantly. We're just swapping the contents. This means whether you have 10 posts or 10,000 posts in your data set, the memory usage for the views is exactly the same. It's constant. It's the only way to build an infinite list.
One last performance trick mentioned here, adaptive quality. We mentioned not downloading 4K video, but how does the app know what quality to download?
It has to be context aware. The app checks 2 main things on the fly: device class and connection quality.
Device class, you mean like iPhone versus Android?
More specific than that, is this an iPhone 16 Pro with a powerful processor? Or is it a 5-year-old budget Android phone? The budget phone might choke on high bitrate video even if the internet connection is fast. The processor can't keep up.
And connection quality is obvious, Wi-Fi versus 3G or 4G.
Right. So the client sends this context to the server with its request, or it selects the appropriate URL from a list the server provides. I'm on a fast phone, but a slow network. Send me the low-res video. Or, I'm on a fast network, but a slow phone. send me the high-res image, but maybe disable the fancy animations.
So it's a whole matrix of decisions happening constantly to ensure the best possible experience for that specific user in that specific moment.
That's the goal, a tailored experience.
This has been a massive breakdown. Let's zoom out and try to look at the whole picture from start to finish. We started with a simple idea, a list of posts.
And we discovered that to do it right, at scale, you need, well, a symphony of engineering. It's not one thing. It's a dozen things working together.
We chose REST over GraphQL to leverage the power of internet caching. We chose cursor pagination to avoid the drift of a constantly changing live feed.
We built a client architecture based on unidirectional data flow, so we never lose track of our state. We made it predictable.
And we implemented a local database as the single source of truth to make the app work perfectly, even in a subway tunnel.
We used optimistic writes to lie to the user about speed, making interactions feel instant, and then back that lie up with a resilient retry queue using exponential backoff.
And we optimized the rendering with native text parsing and view recycling to ensure we never miss one of those 16 millisecond frames and cause jank.
Right.
It really highlights something I've been thinking about this whole time. The best technology is invisible. When I use a really good app, a smooth app, I don't think about any of this. I don't think about the retry queue or the Snowflake IDs. I just see my friend's photo.
That is the paradox of our profession. If we do our job perfectly, nobody notices we did anything at all. It just works. The only time you notice a system engineer's work is when it breaks.
We are the invisible janitors of the digital world.
I'll take that title. I think it's an accurate one.
I think that's a great place to wrap up. So here's a final thought for you to chew on. Consider the sheer amount of engineering magic that is required to make a simple timeline feel, well, boring and reliable. When an app works perfectly, you don't notice the exponential backoff strategies or the database eviction policies running silently in the background. The best design, truly, is invisible.
Well said.
Next time you're doom scrolling at 2 a.m., maybe pause for a microsecond and appreciate the cursor pagination keeping your place in that infinite stream.
And appreciate the local database, saving your data plan.
Thanks for listening to this deep dive. We'll catch you on the next one.